Welcome back to an introduction to real analysis. Here in chapter 3, section 5, we talk about limits at infinity. So previously, we had extended the definition to the limit of a sequence being a number to account for the limit of a sequence being plus or minus infinity. We're just going to do that now to talk about limits of functions to include plus or minus infinities in various ways. It's going to be pretty light on details. This is just a lengthy sequence of various modified definitions. So we avoid defining what it means for plus or minus infinity to be a cluster point of a set. It ends up being equivalent to just saying unbounded above, unbounded below. And in defining infinite limits of sequences, the crucial idea is that a sequence going to L requires the distance from xn minus L to be eventually small. But it is meaningless to say that the distance of xn to infinity is eventually small because those aren't even numbers, and you definitely don't want to think of it as a small number. So the definition of a sequence going to plus or minus infinity was defined in terms of the sequence being eventually large. In other words, eventually larger than any arbitrary cutoff point, or less than if you had a minus infinity as your limit. And we're going to take the same notion of replacing distance to thing is small with bigger than a certain quantity or less than a certain quantity if we're involving plus or minus infinities. That's the general theme of how these definitions get modified. For example, suppose you have a set which is unbounded above, and L is a fixed real number. However, you assume that for every epsilon, there is a cutoff point capital M, so that for any point in the domain past M, the distance from f of x to L is less than epsilon. Then you say the limit as x approaches infinity of f of x equals L. Okay, and it's the same idea as the limit as x approaches A of f of x equals L, except you're not approaching a number A, you're approaching infinity, so you don't have a distance to A being small, you have x being past a certain point. And really, this is the most detail I'm going to give in any of these definitions. Otherwise, they're all pretty much the same theme. Suppose you have an unbounded below set, which is your domain, but for every positive epsilon, there is a cutoff point so that if x is below that, then f of x minus L is less than epsilon in absolute value. Then you say the limit as x approaches minus infinity of f of x is equal to L. Suppose you have a domain and a cluster point of it. However, for any real number m, there is some positive delta, so that if you are within delta to the point C in the domain, then f of x is past that cutoff point m. Then you say the limit as x approaches C of f of x is infinity. Suppose, very similarly, you approach a cluster point in the domain, you are less than delta from that cluster point C. That implies f of x is less than or equal to your arbitrary cutoff point m. Then you say the limit as x approaches C of f of x is minus infinity. You can also combine various infinities. What do I mean by that? Suppose you have a domain which is unbounded above. Then, if for any real number m, there is another cutoff t, so that if x is in the domain and past t, then f of x is larger than m. Then, as x goes to infinity, the limit of f of x is plus infinity. So here, we are taking x past a certain point in the domain, x going to infinity, and f of x being guaranteed to be bigger than an arbitrary cutoff m, so in the range we are going to infinity. And you can combine this to say the limit as x approaches infinity of f of x is minus infinity. The only thing that changes from the previous definition is you want f of x to be below a certain cutoff. And you can get the limit as x goes to minus infinity of f of x is plus infinity. You want f of x to be above a certain cutoff for all x's below a certain cutoff. And you can have minus infinities all around. You want f of x to be below a certain cutoff for all x's below a certain cutoff. All of these definitions are functionally the same idea. It's just formally, we kind of have to list them all out. But once you understand how infinity is played differently than a real number in these definitions, it's all the same thing. So there's a lot of similarity between these definitions. And as I said, we're going to be quite light on details here. If you are familiar with the standard definition of a limit of a function being a number, the only changes that really happen is if you are approaching plus or minus infinity in the domain, you don't want to talk about being close to infinity in the domain. Instead, you say past a certain point if you're going to infinity, or to the left of a certain point if you're going to minus infinity. If you replace your limit with plus or minus infinity, you can't really talk about values in the range being close to infinity. But the same idea. If you want to go to plus infinity, you need values in the range to be bigger than or equal to an arbitrary cutoff, or to go to minus infinity, values in the range to be less than or equal to an arbitrary cutoff. You can throw even more variations into here, so we're not going to formally define one-sided limits going to plus infinity. Okay, I think once you get all of the previous ones, it becomes clear how you would modify these definitions. We've made enough variations that the point gets across. Okay, so we're really just going to restrict ourselves to the ones we already have in here. One first order of business is to establish these limits are unique. This is something we've kind of had to do every time we have an equals sign, just to justify that the equal sign is valid. So in any variation of limit equals number, where you can have plus or minus infinities in one or both place, if the limit exists, then it is unique. We're going to omit the proof. We would also want to get similar results to what we had regarding limits of sequences, including stuff that has to do with composing functions. So suppose you have a function, its domain is S, various things are going to get thrown out. C is either a cluster point of S or a plus or minus infinity when S is unbounded above or below. L is either a real number or plus or minus infinity. Then we write the limit as x approaches c of fx equals L if and only if the limit as n approaches infinity of f of xn equals L for all sequences xn in the domain S such that xn goes to C. And remember, C could be plus or minus infinity here. This just takes an earlier notion for the specific case where C is a cluster point and L is a real number and says, really, this all extends. And we're not going to formally prove it. Suppose F maps the set A to B and G maps the set B to R. Suppose that the limit as x approaches A of f of x is B and the limit as y approaches B of G of y is equal to C. Also, if B happens to be in the set capital B, then G of B equals C. Then you can compose the functions G of f and get this following limit. And you can replace any of A, B, or C with plus or minus infinity, and that doesn't change the validity. That justifies why we had this in here before, if little b is in the set capital B. If b is plus or minus infinity, then it wouldn't be. Okay, so assuming everything exists, then this works out just fine. And proof omitted. So the omitted proofs are not complicated. It's really just a matter of laboriously going back to how the related earlier theorems were proved and seeing how you have to change the proof to account for some infinities being thrown in, because the definition changes in very predictable and repetitious ways. Okay, whenever you have one of these plus or minus infinities, you can't talk about being close to infinity, so you replace it with bigger than or smaller than an arbitrary number, and so that just minorly changes how the proofs go. Okay, so this section really quite quick to get through. We're just going to now throw a few examples out there. For example, the limit as x goes to infinity of 1 over the absolute value of x plus 1 is 0. So the limit is 0, which is a real number, but x is approaching a non-real value. So in the domain, you can't have this assumption x is within delta of infinity. Instead, let a cutoff be given by 1 over epsilon and assume x is bigger than that cutoff point in the domain. Well then, if x is bigger than t, then the absolute value of x plus 1 is also strictly bigger than t. And then here you have it, because remember t was 1 over epsilon. Not much to it. This is an example of how you just have to change your approach when an infinity gets involved. We weren't going to assume that the absolute value of x minus infinity is less than delta. That doesn't make sense. So you use this modification. Another example, the limit as x goes to infinity of sine pi x doesn't exist. So let's define two different sequences, 2n plus a half, 2n plus 3 halves. Both xn and yn go to infinity, but sine of pi times xn is always 1, and sine of pi times yn is always minus 1. So we have two sequences in the domain converging to the same thing. It's just in this case, it's infinity, not a real number. So we can't have a limit because in the range, one sequence is staying 1 and one is staying minus 1. There are some notational conventions worth pointing out. We claimed that the limit as x approaches infinity of sine pi x doesn't exist, but you can definitely write the limit as n goes to infinity of sine of pi times n equals 0. What's the difference? Typically, when we have an n, we're imagining natural numbers. And if n is a natural number, pi times n, the sign of that is just constantly 0. But when you see an x, you tend to think real number, and then the definition of limit is different, and that limit won't exist. So when the notation isn't clear, one should clarify. So you can write, for example, the limit as n goes to infinity of sine of pi n, where we mean n is a natural number. So we have 2 lines of subscript here. Another example, the limit as x goes to infinity of 1 plus x squared over 1 plus x is in fact infinity. So now we have an infinity both in the domain, so to speak, but also in the range. So the claimed limit is infinite, so we don't say I want to be within epsilon of anything. We say for an arbitrary cutoff, we want to be bigger than that in the range. So let m be a real number. We want to show we are bigger than m in the range, at least for x's past a certain t. And we're going to let t be given by the maximum of 2m plus 1, or 1. This little thing, you want to imagine m being very big. So this is generally what will be the bigger thing. So this is just here as a sort of safeguard. If x is at least as big as t, x is definitely at least as big as 1, because that was one of our choices we took a maximum of. But also x over 2 is strictly bigger than m, because t is also at least as big as 2m plus 1. So putting that together, first of all, 1 plus x squared is bigger than or equal to x squared. No big surprise there. 1 plus x is less than or equal to x plus x. So with that in the denominator, we maintain the bigger than or equal to here. X plus x is just 2x. Now I can cancel that out, and x over 2 was bigger than m from right here. So as long as x is past a certain cutoff in the domain, our corresponding value in the range is larger than our arbitrary m. Another example, the limit as x goes to infinity of e to the x minus x squared is 0. We're going to rely on 2 elementary limits that we're not formally going to prove. Specifically, the limit as x goes to infinity of x minus x squared is minus infinity. This does have to be proved, but let's roll with it. Similarly, as y goes to minus infinity, e to the y is 0. We've actually never formally proven any limits involving an exponential function. But again, we're just taking this for granted. So the former one is quite easy. The latter depends on how you've actually defined what exponential functions are. However you define exponential functions, that limit typically gets discussed. So we're just kind of presuming that both of these are in our tool belt. Well, now we're just composing together the x minus x squared function with e to the y function. Since this is going to minus infinity and e to the minus infinity is going to 0, overall we are going to 0. So as a review, we've really just collected a bunch of modifications as like this long laundry list of new definitions, but it's really just one idea. If you are comfortable with the original definition of how limits work, there's not a whole lot to say here, which is why we've blazed through it pretty fast. If, however, you're not familiar with the original definition of limit, you don't patch that up here. Go back and review the earlier sections.